All right, hey there, pre-calc. We are on day 2 of the very first lesson in chapter 1 here. I know it says 1, 2. We skipped over the first one. That's all right. That's all right. So here's what we're going to look at. We're going to build on the idea of things you did in Algebra 2, things were continuous. Okay, and all that means is that if you put your pencil on the graph and you go left to right, that you never pick up your pencil. That means that there is no place that this function does not exist, or they are all one after the other. They're not jumping around like we're about to see. Okay, so that's continuous. Discontinuous. It could be just at some point that something is either has been removed and it doesn't have a value, like this point here, or it has been removed and it just has a different value. Okay, so in these, we kind of trace along. We have to stop because it's somewhere else, and then we come back and we can trace along. Or we're going to trace along and then we skip over it. So this is just looking at the graph. It's the very first thing that we're going to deal with. And our third one here, so our non-removable, okay, so this is where things, as we factor tops and bottoms and all sorts of stuff, we find out that we just couldn't take it out, right? Non-removable. Okay, removal is we're going to be able to factor something out. So here, we're going to start here, and then all of a sudden, we're going to jump up to this point. Okay, and this one gets a little bit hairy as far as identifying if it's a function or not. Remember vertical line test. Since A down here is open and this one is closed, it still passes for a function. So it's kind of neat and unique in that manner to really test that idea of functions versus relations. Okay, so that's our jump discontinuity. And then infinite, this is where we start bringing in those vertical asymptotes. Okay, so we call those VAs, vertical asymptote. And here this would be at x equals, let's say that's 1 for example, because that's that vertical line that we have. And that means it's infinitely has discontinuity. So what happens is we're going to find a value that x simply cannot be. It doesn't matter. And that's going to break up the graph into 2 different branches. And we'll work forward from there. Okay, so we have infinite jump. We have just by one single point, and we have completely continuous. Okay, so we'll kind of look at these. I stole these out of the textbook here just to give you an example, and we can start to tie some ideas together, although we don't have to do anything with it at this point. So we know in the denominator, I simply can't have 0. So I'd find out where it makes it 0, and then I say x cannot be 2. So look what happens here is where x is 2, we see these branches of the graph bending around there, and it simply doesn't touch it. Okay, so that gives us a vertical asymptote at x equals 2, so we can identify what's going on. So that's getting a little forward of where we need to be, but we just want to know that this is discontinuous. When we look at the next one, we know this is going to be x times x, so it's going to be an x squared, which makes it a parabola, a happy little parabola, and we can trace the whole entire thing. So this one is continuous. So I might say discontinuous here. Here we're going to say continuous. All right, and then our last one, we see this hole in the graph right here, and you're thinking, how did that happen? So I had x plus 2 and x minus 2 as I factor the numerator, x minus 2 on the bottom. So what happens is I can't use 2, but then it's not just something where I can't use it like we did over here on the left. This one is actually removed. So we start to get the idea of removable means we're going to take it out, just like when they make a donut. They actually make the whole circle, and then they use a punch to take out the middle. So we're removing that hole, and that's how we come up with the donut hole, which is just as delicious as a regular donut, and it's less messy. So I like that for the kids in the car and while I'm driving a lot. All right, so this is also going to be discontinuous, and then we can work on that it's removable so we know what it looks like. All right, continuous, discontinuous, that's the first thing. All right, next thing we're going to do is we're going to find out where the graph is increasing. Notice I have on here a note left to right. Okay, so just like you read your text, we're going to work left to right. So we're always going to put a pencil on it, kind of trace it. Use the highlight here. So at this point, I'm going up, 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 up. It starts to level out, but it's not level. It's still going up slowly. So this function is increasing the entire time versus our next one. Looks like an exponential here. So we're going to come down. Okay, it's still decreasing, right? It's going to decrease. It looks like it levels out, but it's decreasing the entire time So we have increasing and decreasing. The next thing that can happen is we can have a constant function. Okay, so this is just y equals 2, right? That horizontal line. So it doesn't matter what x value we have, y is always going to be 2, right? Because this is 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, right? The answer is always consistent that it's always 2. All right, then we can have a little bit of both. So let's take a look here. So when we look at the first section, as I trace it, notice my pencil's going down. So that's decreasing. So we assume this had an arrow on it. Okay, so wherever it started off from, it continues to decrease until we get to -2. At -2, now it starts to level out. So now it's constant. And then after that, I'm out of colors. Let's use this one. It's going to increase from there as we get the other half of that neat little shape that we had. Okay, so we could put that function together kind of piecewise as we did in Algebra 2. Okay, so left to right, we're going to, again, put your pencil on it or your finger on it and just trace it over. Say, am I going up? Am I staying flat? Or am I going down? So decreasing, increasing, and constant. All right, so from the graph, it's kind of easy. We don't have to do too much. As long as you remember left to right, it's not that bad. But when we start looking at a table, then it's a little bit different. Okay, so I'm going to say, is it increasing, decreasing, or constant? And these are all going to be one way to make it a little bit easier. But notice in my first column, it doesn't matter what value I use, I keep getting 12, right? It's a change of +0 each and every time. Okay, so that means this is going to be constant. When we look at the next one, right, this is going to go down 2, down 1, down 2, down 4, down 6. Now, I'm not looking to see what type of function is. I just want to know if it's increasing or decreasing. But what happens each time is the values are going down from the last one. So that makes this decreasing. And in the last one, I got +2, +2, +2, +3, +6. All right, so I don't need these to be the same. But what I notice is each and every single one of them is plus some number. So that means this function is increasing, at least from -2 to 7. So for the snapshot that we got, it's definitely increasing. Okay, so increasing, decreasing, and constant. All right, last thing for today. Oh, nope, 2 more. We got boundedness. Boundedness is only going to deal with range values. So what's that mean? That means we're talking about the y values. So I'm looking at the graph and I'm trying to see, can I stop this graph by putting a line on the top and the bottom? Well, it's not bounded above and it's not bounded below because these are assumed to be continued down and up. Okay, so it's not bounded. So I try again to put some boundaries on the top and bottom, kind of like your sidelines in volleyball, football, whatever you like. Okay, so we know I would go through the top, right? But the bottom is going to stop right here. So it is bounded below. The next one. So we would start by just throwing some horizontal lines on there and kind of see what happens. So this time we know this is going to continue down, but on the top it does stop, right? We have some maximum values right there, or turning points, but it's not bounded below. So we're very specific about saying above or below, and then what happens in front of it. And our last one on here, top and bottom, look, all the points stay within those values. We don't care what the values are at this point. That's the next section that we talk about. Okay, but we know that this one is bounded because we can put a limit to the top and a limit to the bottom. Okay, so again, the big thing here is range values. Okay, so we dealt with horizontal lines. All right, so some things we might find in here. If we want to find some local extremes, right? These are your local maxes and mins. We just want to take a look at each of these values. So P and R, they're at the top of those things. Okay, so those are going to be the local max. P and R. And Q is going to be a local min. Okay, so here's a screenshot from what you might find on your calculator. So we have a minimum value. Right? We have also a turning point, right? And it turns again here and here. Okay, so I get two minimum values. So I'm just going to circle those and say mins. Okay. And then this one up here is going to be a max. Now, if we want to go through and find out all the decimal values in the calculator like this, we could do that. What I did is I took an equation, I threw it into Desmos to try and illustrate the same thing, but I also clicked on those things. All right, so our minimum value, and I'm going to tie the y value to it, because once we start talking about these to get actual minimum values, so these are local mins, that means the y value would be negative 24. Okay, so this is a min, this is a min. Okay, so of course the other one being up here, and again, it's still about the y value. X tells me the location, but the y value tells me the actual maximum value for that turning point. Okay, so that's the maximum value we can get. So this appears to be the bottom of the entire function. Okay, so that's the lowest value you'll ever get for whatever function I just pick some numbers and throw them in here. So whatever we get, that'll be our lowest values, and then we move up from there. Okay, so trying to keep everything here just kind of baby steps. So we're going to give 21 to 40 all. Okay, I do have some answers in your OneNote, so you can double check, make sure we're doing okay, and bring your questions to class.